Okay, thanks for showing up. So I'm covering lecture 3. I actually changed the title. The title was Regression and Classification, and I changed it to Classification and Regression because we'll talk about classification first and then about regression. And I'm doing it in this order because I think classification is the simpler problem that also has actually more things to worry about. It's kind of both simple and more complex at the same time. If you've taken, who has learned classification and or regression in a stats class? Okay, there's always at least somebody who hasn't learned the stuff that you're presenting. That's good. Like most of you will just already know everything, but I saw also some like, I don't know if I've learned. If you talk to a statistician, they will tell you all of machine learning is just classification and regression. There's really no difference between a linear model and like a 2 billion parameter neural network. It's basically the same thing. It's of course not quite true, but it's surprisingly true. Most of the concepts really carry over. So let's talk about classification first. So I've made a very simple graphic. So let's say like there's these shapes, we have circles and we have squares. And maybe we want to identify, like we want to have some algorithm that can say this is a circle and this is not a circle or this is a square. And importantly, what the algorithm should be able to do, it should be able to do this without worrying about the size or the color, right? Like that's a typical classification problem. We have some characteristic that you care about, and you hope that you have some computational method to identify or predict whether something is, say, a circle or square, while disregarding the things that you don't care about. So that is classification. Now, some examples that, I mean, there's like millions of examples, but just some examples of where it could come up. The most canonical one is you want to predict whether somebody or something is diseased or healthy, right? Like anytime you do any sort of medical test and they say you're positive or you're negative, like you take a COVID test, it's basically a prediction of are you likely infected or not. So it's a very simple classification problem. If you want to go to chemistry, like you may want to have some computational method to predict whether some compound is going to be active or not. That would be a classification. And like the canonical one, like you want to identify whether you have a cat in an image or something else, right? I wrote cats or dogs, or it could just be cat or not cat. So those are all examples of classification. Okay, so now regression. So still in my example with shapes. So if you look at this for a while, do you see something here that could be a regression? Like, can you identify the regression problem that I've created? Okay, number of sides on the shapes, and regression has 2 variables. Okay, what do you think is happening? Yes, correct. Right? And so again, we want to abstract over, well, really the only other characteristic here is the color. The color doesn't matter, but I drew it such that the number of sides is directly proportional to how big I drew the element. And so that is a regression problem, right? You can predict, if I tell you now, well, I drew a new polygon and that has 25 sides, then you could extrapolate this line and you could say, well, this is where I would expect it to be. And that's a typical regression problem where you have one quantitative variable, or actually one or more, and it doesn't even have to be quantitative. But the important thing about a regression is what you're predicting is a quantitative thing, right? It's a number, like it's size. And like there's always the question, how do you tell whether something is a categorical or a quantitative variable? And the very simple test is, can you add or subtract them, right? If I have 5 and 7, I can add them and the sum is 12, right? Yeah, I'm not very good with math, sorry. If I have something like, well, for sure, if I have color, I cannot add color, right? I cannot take red and yellow and say, what's the sum or what's the difference? There's a sort of intermediate, which is categorical but ordered. That would be something like grades, for example. And it's funny, we calculate grade point averages, but you really cannot add an A and a B, right? You can convert an A and a B into like a 3 and a 4, and then you can add them. But like, if it's just letter grades, it's ordered, but it's categorical. You cannot add or subtract them. Or if you like, you want to like buy a car or sell a car on like in a private market, and you say, well, this is great, this is like excellent condition, mint condition, or whatever. Again, they're ordered like fair. Actually, I don't know how these things work. Like mint is good, right? Poor is bad, right? So there's an ordering, but again, you cannot add poor and mint, right? In any case, that's a regression problem. We want to predict a numerical quantity based on some attributes that we may have. And then their typical examples are, let's say we want to predict the stability of a protein, right? Not just whether the protein is stable or not, but actually how stable is the protein. That would be a regression problem. Or the activity of a drug. So in the classification, it was just, is it active or not? In a regression, it would be, no, this is how active specifically it is. And then the last one, just to show that like very complex things can still be regression problems, like predict the size of an animal when grown from its genome sequence, right? You have the genome sequence and you want to know, like, there's like small dogs and large dogs, right? In principle, you should be able, and it's fully determined or mostly determined by their genome, right? Small dogs, when they make baby dogs, they're also small, right? There might be some maternal effects, but mostly like there must be something in the genome that predicts the size, right? So in principle, maybe we can't do it today, but in principle, we could write down a regression problem where the input is the genome and the output is this a large dog or a small dog. Okay, so those are various regression problems. Now let's go a little more in depth when you actually do this, what can happen. So let's go to the classification. When you classify, you make correct predictions, hopefully, but you also sometimes make incorrect predictions, right? So now we go back to, is something a circle or not a circle, right? On the left are the circles, on the right are the not circles, and you probably see that I made some mistakes, right? That was on purpose. So these we call true positives. So they're circles, and I called them circles, right? This is a false positive. I called it a circle, but it's actually not, as far as we know. And then the same here, this is a true negative, not a circle. False negative is, it's a circle, but I said it's not. So I think intuitively can immediately understand that if the things that I call circles mostly are circles, that's good. And if the things that I say are not circles mostly are not circles, that's also good. And the number of correct versus incorrect predictions, that must somehow tell me how good my model is, right? It's okay if I make a mistake from time to time, but if I mostly make mistakes, then something is wrong. Okay, and so then we count, okay, how many true positives, how many false positives do I have, and so on. And that is then a measure of how good my model is, and that's great in principle. And in practice, this is the most confusing part of this whole world, because there's so many metrics, and they all like sometimes the same metric has different names, and sometimes very similar sounding names are different metrics. Like if you go to this Wikipedia page, sensitivity and specificity, these are all the different metrics that people use, right? Sensitivity, recall, hit rate, or true positive rate, that's all the same first thing, right? And then we have specificity, selectivity, or true negative rate, and just goes on and on and on. It's okay if you're confused, I'm confused, but let's look at just the most, maybe not the most, but very commonly used metrics. The first one, and it has already 3 names, right? Very helpful. Call the same thing 3 different ways just to really confuse you. Sensitivity, recall, or true positive rate. So what I wrote here, TP, TPFN. So this is basically just the count of the these are the true positives. So how many circles did I call circle? That was 5 in the graphic that I had, divided by the true positives plus the false negatives. And that, if you see that for the first time, can be confusing. Why do you take the true positives and the false negatives? Well, the false negatives are the circles that you incorrectly predicted are circles. Well, you said it's not a circle, but actually it is a circle, right? So the denominator is actually all the circles, basically. The denominator is all the things you were looking for, and the numerator is the things that you found, right? So it's basically the fraction of things that you correctly predicted of all the things you were looking for. So fraction of all positives that are correctly identified. And that's why it's called the true positive rate. So that tells you something about how good you are at finding the things that you want to find. And that's why it's also called sensitivity or recall, right? Recall is, are you actually finding the things you're looking for? Obviously, you want this to be as high as possible. Then sort of the opposite is the false positive rate. So that's a fraction of all negatives that are incorrectly identified. So we're taking the false positives. So it's not a circle, but I incorrectly call it a circle. And then I divide it by the false positives and the true negatives. So these are all the not circles, right? So this is, in a way, this is the opposite. This is like the fraction of things I get wrong among all the things that could have been classified incorrectly. So false positive rate. And of course, that you want to be as small as possible, right? The true positives you want to be as large as possible. False positives you want to be as small as possible. Now, there's a third metric that is very easily confused, in particular with the first, which is the precision or positive predictive value. That's the fraction of true positives among all positives. So this here was the fraction of all positives that are correctly identified. This is a fraction of true positives among all positives. So the denominator is different, right? So here I have the true positives and the false positives. So here I'm asking, when I call, like, of all the things that I call positive, so the true positive and the false positives, how many are true positives, right? I said 6 things are circles, 5 of them actually are circles. So the positive predictive value is 5 divided by 6. So a high positive predictive value says when you call something a positive, chances are it actually is a positive. The true positive rate does not tell you that, right? The true positive rate tells you about your ability to find positives, but you can have a great true positive rate, right? The false positives don't enter this at all. You can have a great true positive rate, but tons of false positives, right? Like the classification problem that I like to use as an example, because it's immediately obvious how problematic it is when you get these things wrong, is like security check at the airport, right? The goal is to find a bad guy with a gun, right? How often do they find a bad guy with a gun, right? Almost never, right? Because like in the grand scheme of things, there's not that many, right? I mean, there's thousands of people every day just in Austin. I'm sure most days they don't find even one, right? So that is actually good in a way. So they could get a really high true positive rate if they call everybody a bad guy with a gun, right? If everybody who shows up, they say, yeah, you're a terrorist. We don't let you on the plane. They catch all the terrorists, but they have a terrible positive predictive value, right? Because like most people are not terrorists. Most people don't have a gun on them. So these are sort of different ways of thinking about the problem. And what we'll talk in a minute about, like the specific example that I gave you here is one where you have extreme class imbalance. So they are trying to find terrorists, but most people are not terrorists, right? So the positives are extremely rare. That's actually a very complicated problem. It's a much simpler problem if the positives and the negatives are roughly evenly distributed. Okay, so now with these 3 methods, so again, if we go back to the example of, should I stick to the, let's stick to the like example of the terrorist at the airport. There might be some, like there's extremes, right? On the one hand, you can just say, I call everybody a terrorist, and I'm sure I catch every terrorist. It's not a good classifier. Nobody ever flies again, but I've caught all the terrorists, right? That's one extreme. The other extreme is, I really don't look that carefully. Like I let everybody through. There's this funny GIF that some of you may have seen of a guy, like the guy swiping people down at the entrance of a concert, and he's not swiping at all, like just sort of going down and letting through. Who has seen that GIF? At least some of you have seen it, right? So that's the other end. It's like, yeah, go through, I don't care, right? And then there's sort of, is somewhere in between, you have sort of a cutoff, right? You can be more or less strict. And that's a general property of any classifier. And so that means we can sort of sweep the entire space of true positives and false positives. So I can call everything positive. So here's my true positive rate. If I catch all the positives, the true positive rate is 1. And I can reach that by calling everything a positive. But then I've also called all the negatives positives, and then my false positive rate is 1. And then, like usually, like in these models, there's some sort of dial that you can turn, and so you can choose where along this curve you want to be. And here the diagonal says random classifier. So that is, you're just randomly calling things positives and negatives. And so then on average, for one positive, you get one, like for one true, you get one false. And so that is a diagonal that is exactly going diagonally from 0 to 1 here. And any classifier that actually does something meaningful does better than this. The perfect classifier would be up there, where it finds all the positives without even like making one single mistake. And in practice, there's somewhere along this curve. And so the faster they rise, the better. Right? You want to get as many correct classifications as you can with as few errors as you want. And people draw these. This is called ROC. ROC stands for Receiver Operating Characteristic. I don't really, does anybody know why? It's a really, really old term. Yeah. Okay, can you explain it? Okay. In any case, that's what it's called. And people like calculate the area under the curve, and like the bigger the area under the curve, the better the classifier. Okay, so this is good. Like many people use it to assess the performance of the classifier. One problem that arises, I mentioned this earlier, is if you have extreme class imbalance, right? If you have only very few positives, then maybe you don't care so much just about the true positive rate and the false positive rate, but also your positive predictive value. How many of all the things you call positive, how many actually are positive? Actually, yeah, I like to do the airport example, but another example where this comes up a lot is if you're testing for rare diseases, right? If any test has some fraction of false positives, if you like, actually cancer screening is a very common problem. If you screen everybody for cancer, you oftentimes get so many false positives that like more people are like falsely predicted of having cancer than you're actually finding, right? Like that's why, like, I think they recently reduced the recommended rate of breast cancer screenings, because if you do it too much, you just find like women with cysts or so that don't really have breast cancer, but like you screen enough, you find like many false positives. And so you also care about the positive predictive value, in particular if what you're looking for is rare. And so then there's this alternative curve, which is called the precision recall curve. And now if you remember from previous, recall is exactly the same as the true positive rate, right? So what on the other graph was on the y-axis is now on the x-axis is the recall, is the true positive. So you want to end up here eventually, but the precision, that's your positive predictive value. That is how many of all the things that you call a positive, how many actually are. And ideally, you start there at 1. That means at least when you don't recall a lot, you get everything right. But a really bad classifier could already start out way down here. So that's the advantage of this precision recall curve. So again, like you're looking for the area under the curve to be as high as possible. Like the ideal one here would be all the way flat on the top and then fall off. But the advantage of this curve is it can start somewhere other than 1 there. What I don't like, it's just like, I don't like it so much that they have like, these curves always have these weird spikes and they go up and down, and I don't like it. My problem. Like our C curves are always nice and smooth, and precision recall curves have all these weird, yeah. So the recall was here on the x-axis is the exact same thing as on this one on the y-axis. If you go back to the definition, sensitivity, recall, true positive rate is all the same. And this is what I meant with it's so easy to get confused. Like not only are there so many metrics, they also have like the same metrics have different names, right? And like this is always like whenever I see an RC curve, people talk about the true positive rate. They never say recall in the context of the RC curve. But the precision recall curve, it's always the recall, right? And then in other contexts, people talk about sensitivity and specificity. And it's again, the sensitivity is the recall. And specificity is yet another metric that we haven't discussed. Okay, so yeah, these are preferred when they're class imbalances. Or some people, like Edward McCord loves precision recall curves. So his papers always have precision recall curves. And that's fine. I mean, there's nothing wrong with preferring this or the other one. Really, they're all like, ideally you want to have multiple of these metrics and they sort of all should be consistent, right? Okay, so now the linear regression there, the evaluation is actually very straightforward. It's simply, so in the simplest case, we fit a straight line, but in more complex cases, we can fit a curved line or a surface. In any case, we predict a numeric value, and then we generally have an actual value, right? I predict how large the dog will be from its genome, and then the actual dog might be a bit bigger or a bit smaller. And that might also depend on whether the dog gets a lot of food or not. But so it might not even, like, even if your model is perfect, there's still going to be these errors that are caused by other things that your model can't account for. And then you calculate the root mean square error, which is basically you just take all these differences, you square them up, and then you add them together and calculate the square root of that. And that's basically something like the mean distance of each data point from the predicted value, right? And so if your model is good, the mean distance is small. And if your model is bad, the mean distance is large. And then oftentimes we calculate this R squared. R squared is, so R squared is the square of the R. R squared tells you the amount of variation in the data that is predicted by the model rather than by the error. And so a large R square, we usually express it as a percent. So an R square of 100% means the model is perfect. R square of 0 means the model doesn't work. And so, so large R square or large R, the data points are very close along the line, and low R square or low R, they're more dispersed. And then if you don't square it, there's also a positive or negative sign, but that's really specific to correlation. So let's just leave it at that. So in general, in a regression, because you're predicting numerical values, there's a very simple metric that just says how close are the predicted values to the actual values. Okay. So now under and overfitting. So far I've told you what these models do. And if you've paid attention, you may have wondered, well, how do I even know whether something is a true positive or false positive, right? If I predict whether something is a circle or not, but if I don't know whether it's a circle or not, how can I tell whether my prediction is right or wrong, right? So this is a fundamental problem, like maybe more obvious. Again, if you you test whether somebody has a disease, like you test whether they have COVID or not. Okay, you run the test and the test says, yes, you have COVID. How do you know whether you actually have COVID, right? So this is a problem. And then, and we'll talk about that in a second, but so then related to that problem is you can make a model that so you need some sort of data set where you actually know the ground truth, right? And where you can assess, like say with a clinical test, usually you have another test that tells you whether somebody truly has COVID or not, and then you can use that to check your new approach. And that means you could overdo it. So let's say in the classification problem, let's say we have these colored dots in a plane, and our goal is to determine whether the dot is likely blue or orange, right? And here what is called the right fit. So it seems to be in the lower left corner, the orange, in the upper right, the blue, and some sort of separation like this is probably right if we assume there's maybe a little bit of diffusion of these colored dots at the boundary, but mostly this is the boundary. This would be a bad boundary. I mean, it helps separate the orange and the blue, but maybe if the boundary looks like this, we would have caught a few more orange points. But this is certainly overdoing it, right? Here I'm like fitting the boundary exactly to the points for which I know the color, right? But I might very well have an orange point here the next time I get one, and this model would say it's blue because it carved out this special allowance for this one here, but this really should have been an error, right? So this is overfit, this is maybe the right fit, and this is underfit. Underfit is not really a problem, it just means you could have done better. I'm actually a big fan of underfitting, which we'll see on the next slide. And yeah, so now we can do the same for regression, right? And this is now a regression where really the correct model is maybe nonlinear. So something like this would be a good fit. This is terrible, right? I'm capturing all this variation that really should be error. It shouldn't be like this. This is underfit. I'm just fitting a straight line. And this is what I meant with I'm a big fan of that. Like oftentimes this is perfectly reasonable to do. If there is an overarching trend, you capture the overarching trend. And the advantage of the linear model is it's extremely simple. It's just a straight line. You can always fit a straight line. You rarely make a mistake. So this is very safe in a way, versus here, like the moment it's curved, you have to worry about, okay, what is the functional form? How many parameters do I use? And like in a linear model, you don't have to worry about overfitting, right? And so people oftentimes get too hung up with, well, but it's not perfectly linear, so what? Like just fit a linear model and see how far you get, right? Only go to the nonlinear model when you really have evidence that the linear model does work. So don't worry too much about underfitting. Like if you're underfitting and you get workable results, great. It's better to be on this side than to be on that side. Okay, so how do we do this in practice, right? So to prevent overfitting, what we need to do, because remember, so we want a model that can make predictions on unseen data. Like I want to have a test. Let's say if I want it computationally, like let's say my goal is to like I have an app on my phone. I just look at the camera and takes a picture and says, do I have COVID or not, right? Maybe that's not possible. Let's say that's my goal, right? And I train that app on a set of people where I have the pictures and I know, like using some other tests, whether they have COVID or not. So all data is all the data for which I know the ground truth. Then I want to split that into training and test data. And then what I do is I define hyperparameters, which just means that's just the choices that I can make in what model do I want to fit. Like, let's say if I'm fitting a regression model, okay, how many predictor variables do I use? So is it linear versus nonlinear? And all these kinds of things. Those are the hyperparameters that just define the model setup. Then I train the model on the training data, and then I test the model on the test data. Great. Okay, let's say I do this, and I'm not really happy with my result. And so then I define other parameters. Let's say I did a linear model. Now I try a nonlinear model, do it again, test. Still not quite happy. Maybe I need a random forest model, which is like another statistical model that you might want to do, and do that. Is there a problem with the procedure that I just described? And you shouldn't answer if you're an expert in machine learning. But if this is sort of new to you, think about what I define a model, I fit it to my training data, and then I test. And then I say, well, maybe I can do better. And I change my model setup, I fit again, and I test. Is that okay, or does that create a problem? It's overfitting. Why am I overfitting? I'm testing on data that I didn't train on. Yes, so you're exactly sensing what the problem is. So one way why do we do this, right? So what we want to prevent, I go back here. What we want to prevent is scenarios like this, where maybe there was an orange point here. I didn't see it in my training, so I thought this was a good idea. But then if in the test it's orange here, that would be counted as a mistake. And that would tell me that the model just is maybe not a good model, right? But the test data has some like certain structure that it just happens to have based on how you subdivided the data into training and test. And so if you now iterate through models, that's also a form of fitting, right? And so if I do this over and over, like I'm actually basically fitting the hyperparameters until they happen to work well on the test data set, right? I mean, in the extreme case, you could end up with a model that actually does terrible on the training data, but really good on the test data, because the whole cycle actually now has turned into a fitting loop if you do it over and over and over. It's probably the most common mistake in machine learning people make all the time, in particular if they haven't really been trained a lot in machine learning. But even if they have, like this, like always my first question, like, did you actually do this? And you'd be surprised how often the answer is yes when you dig in a little. So the correct way to do this is you actually have to split the data even more. You need training data, validation data, and test data. And so what that means is you do this loop of training the model and validating until you're happy with the prediction at this stage. And then in the end, you test. And you test only once, right? And if you wanted to be really honest, you would literally test once, right? And with most of your grad students, right? Which graduate student has tested exactly once, right? None, right? You always think you work on it and that doesn't quite work, and you fiddle around with it a bit, and now it's starting to work better, and so on, right? So that's like, on some level, that's the reality of things. But also, I really want you to be aware of this trap that you can fall into, right? And these machine learning competitions, where they're all like, oh, who gets the best result on this data set? They're basically all just overfitting at some point, right? Like in particular, like I've been sort of machine learning adjacent for like the last 25 years. Like I did my PhD in '99, and it was in a lab or in an institute that mostly did like neural networks and machine learning. And I've tried to stay away from it for like 25 years, because most of, I mean, obviously there has been like massive improvement and it's extremely useful. And now my lab is almost exclusively doing machine learning. But if you look closely what happens in the machine learning field, a lot of it is just people competing over like a slightly better ROC curve, you know, like, oh, my model is 1% better. And they always have the same 1 or 5 or 10 data sets, and they'll write hundreds of papers. Oh, but my paper performs a bit better on this data set that everybody has used. And it's almost certainly primarily this sort of trap of, yeah, your model works really well on this particular data set, and now I want to use it on my data set, and it doesn't work any better than any other model I could have used. Again, so I mean, there's tons of interesting stuff happening in machine learning, but if you're working in machine learning, I would encourage you to not fall into that trap of just competing for 1% better prediction, right? You want to do something conceptually new, or like, yeah. So that's what we call cross-validation. And so we would normally do this on, so I drew this here as training and validation data. So you probably want to have a true test data holdout that you truly don't touch until the very end, right? I would say actually the gold standard, in particular, if you're working in biology, where often what you predict is actually something that could be measured, the true gold standard is you only generate the test data after you've made your prediction, right? My lab just recently wrote a paper with Brian Davies where like we predicted peptides that should have activity, and basically we gave him a new set of peptides and said, we have predicted these to have this kind of activity, build them, evaluate them, did our model do right or not, right? That's sort of the gold standard. And if you do it that way, you truly have not like deceived yourself. So you should always truly hold out test data, but you can take the entire like data that is not your test data and say, well, I use that for validation. So I split the data into pieces, and then each time I take one part as validation and the rest to train the model. So during validation, you always validate on some data that you didn't train on, but you mix it up and you do it repeatedly also because you could always by accident end up with a validation data set that just your model either works really well on or really poorly on. And so you want sort of an average performance, right? If I do this 10 times, on average, is my model doing well or not? And so that's what the cross-validation does for you. Yeah. So that's like you want to make it as big as possible, but whatever experimentally is feasible, right? I would say if you have 10 things, like let's say it's a regression, you're not, actually no, let's say it's a classification. I just want to say, is something working or not? If you pick 10 and 10 random things, almost certainly none would work. 10 is a good number, right? I mean, there's like, wasn't the first either vaccine or antibiotic, I don't remember, like all the rats that didn't get the treatment died, and none of the ones that got the treatment died. Like, you get the treatment, you survive. You don't get the treatment, you die. If you do that on like 10 and 10 rats, that's pretty convincing, right? But if it's something where like maybe by random chance, half of the time it works, and then in your like test data set, it works like 65% of the time, you need way more than 10 to feel confident in those differences. Okay, so we're almost done here. So the last thing that you can do once you have gone through all of this is, first of all, like once you have decided what your optimal hyperparameters are, you can actually retrain the model on the entire training data set to just get the best model that you can make out of your training data, right? I mean, this whole like validation process is just to figure out, okay, what are the exact setups that I want to use? And once you've decided, it's fine to train on the entire training data because the process of choosing those parameters already was training on the entire data set anyway, right? And then you take that and you evaluate against the test data, and then that tells you overall how good your model was. Right? And if you truly do this only once, then it's truly unbiased and a truly fair assessment of your model. If you do it more than once, then if you get reviewer comments and in response to the reviewer comments, you redo everything one more time, then you've already violated. Right? Oh, yeah, and I think that's the last slide. Oh, no, this is the last slide. So the one last thing is, so the one assumption that all of this is making is that when you actually deploy the model, so when you actually use it on new unseen data, that you don't get completely different things that you didn't consider when you were training, right? So if there's like orange and blue things and you train your model to separate them and you get some new orange and blue things, okay, that's what the model has been trained for and it can handle that correctly, but then you get something completely different. And I mean, in this case, if the goal was to predict orange, the model would actually by accident still work. But if the goal was to predict blue, arguably this actually should not have been predicted as being on this side of the decision boundary, right? As being blue. So that's always a problem that in the end, these models, they don't extrapolate very well. And so if you train on some subset of data that maybe has constraints that you're not aware of, and then you deploy in a different context, you may get into this area and you may not even know, right? And then that would be, what happens is then in practice, like the model worked great during the training and test, and then you deploy it and it doesn't work, right? Maybe like a typical example is like face detection on dark-skinned people, right? Like, I mean, these people build these like all sorts of like face detection and scanners and so on, and they work great in the lab, and then a really dark-skinned person tries to. You're fairly dark-skinned. Have you run into those issues? No, but I mean, I've seen it. Yeah. Yeah. Okay. So that would be, but if your oxygen is really low, does it check that? You probably have never tested that, right? But I've seen like posts on Twitter where like really dark skinned people like try face detection or so, and it doesn't work, right? Worst case scenario, it doesn't even find the face. It's like too dark. So that would be a very like typical out of distribution case. And the people building the thing, like, I mean, you run into this because you either didn't think about it or weren't aware was an issue. It just didn't pop up in your training data, right? So yeah, that was the last slide. So we have a few more minutes if there's any questions or comments. Yeah. I mean, so normally you never have enough data to like split it that much, right? And so I think the better strategy is maybe to really like hold out the test data until you feel really confident that it's time to try it, right? You can like all your like iteration and trying models and so on, you can just still hold out a test data set that you never touch, right? Until you feel very confident that you've really started to get a handle on the problem. Because I mean, most of the time this iteration just happens early on, right? You're trying this model doesn't quite work. Let me try this other model. Well, maybe this works and so on. Like there's a lot of like most iteration is early on. And so you don't have to touch the test data at all until you're a little further in. Also, I mean, can be philosophical or we can be realists. Most people probably try that test set more than once, right? And maybe that's okay. Just like there's a big difference between maybe trying 3 different things and trying 300 different things. So you're describing one particular choice, which is the validation loss, right? But maybe you're also trying different architectures, if it's a neural network, right? And oftentimes what happens is you train a model and you get like a validation result that you're happy with, and then you try it on the actual test data, and then it doesn't work as well as you thought, right? And then you're like, something wasn't quite right. And that's when you start doing things over, and that's when the risk comes, right? And now it could actually be that it's really this, right? Like in particular, like what I just described, like a gold standard is you actually go and you do a new experiment, or you have like a truly separate data set. Like you have all these genomes from these sources, and then you have like another set of genomes from this other sources, right? And so on the one hand, it's a perfect test data set because it's truly separate, it's clearly distinguishable and so on, but it may also be this. And you may only discover this once you're testing, right? And then yes, you have to go back because now you've realized everything you've done during training was wrong. But then if you fix that problem just by finding a different network architecture that accidentally like extrapolates to this, that would also not really be right. I mean, that's the truly challenging part of this whole field, right? That's where the real mistakes happen, I feel. And so we can only like describe what is like the ideal world, right? And the ideal world is every time you want to test, you actually collect a new data set that didn't exist before. And the moment you do that on data that is expensive, it's just not going to happen. Okay, was this useful? I mean, many of you I know like are familiar with this stuff. So okay, good. Did you have another question? Whatever the grad student decides. Yeah, you need enough test data to be able to assess whether your model works, right? And that may not require a lot. I mean, as I just said, like the example of where like, if it doesn't work, the animal is dead. If it works, the animal is alive. You don't need a lot of dead or not dead animals to feel pretty confident in your outcome, right? If 5 survive and 5 don't, all the ones that survived got the treatment, all the ones that died didn't get the treatment, you're probably pretty confident that it works. But in more subtle scenarios, you may need more test data. And so like, how much test data do you need to assess whether the model is actually working? Most of the time, it's not as much as people may think. Like if you have a massive data set, even 1% may be enough to test, right? So underfitting is a statement about your model versus the truth, right? That's separate from what data have you actually collected, right? So for example, if we look at this data set, there's sort of a linear relationship here, and then it gets nonlinear here, right? If you only collect this part of the data, then that is linear, but the truth is still nonlinear, right? So this would still be underfit. Like if I mean, so if you fit, you made an example where you fit to the larger set and then you test on a smaller set, right? That would be the same as like only testing, say, in this part of the data. The model is still under, right? But again, I would not worry so much about underfitting, right? Underfitting is only a problem if you don't get the performance that you need. So underfitting is a problem if you're competing on some sort of like data science competition, right? Because somebody else will not have underfit and they'll have 2% more accuracy than you do, right? But in reality, if your model is working well enough and it's underfit, that's fine, right? It's much better to underfit than to overfit. Okay.